All right, let's talk a little bit about error analysis, specifically what is random versus systematic error. So previously we looked at two different types of error. We looked at the difference between absolute and relative error. So absolute and relative error have to do with how to express an error. So absolute error is the actual range in values or the actual uncertainty that you have in your measurement. And it has the same units as the measurement. And relative error is the error relative to the measurement. So that would be expressed as a percent. 25 milliliter if you have an uncertainty or an error of plus or minus 1 milliliter, that is absolute. 1 milliliter is 1 milliliter, that is a measurement. It's an actual value. It has the same units as the measurement. 4%, you don't know what that is unless you also know the measurement. It tells you relative to the measurement itself how much error or uncertainty you have. So these are ways of expressing error. The two we're going to look at today, random and systematic error, are more telling what is causing the error. So random error is variation that you can expect basically just given how the experiment is run, the different equipment that you're working with, how carefully you're taking the measurements. So that contributes to the random error. Systematic error would be caused by a specific problem in the way something's being done, or a problem in the instrument, maybe the calibration or something, that skews the results in one particular direction. These classifications of types of error are independent from each other. You can have random error expressed as a percent or as an absolute, and you can have systematic error expressed as a percent or as an absolute. So here's a little bit more detail on the differences between random and systematic error. For random error, it's just a variation, so you have an even chance of the measurement being too high or too low. So if you take the measurement several times, you should get some that are too high, some that are too low. But for systematic error, the error is all in the same direction. Either all of your error is too high, or all of your values are too high, or all of your values are too low. And so we mentioned how random error is caused by the precision of the instrument or the methods that you're using. And so it's difficult to improve on random error unless you change the instrument or the technique that you're using. And you're never going to completely eliminate random error. You can make it smaller if you improve your precision. Systematic error, since it's caused by a specific problem that is skewing all the results too high or all the results too low, if you figure out what is causing it, you can sometimes fix the problem, or you can correct for it if you notice a pattern. So for example, if you have a scale at home and you notice that whenever you go to the doctor's office, their scales say that you weigh 2 pounds more than your scales at home, then you can just do that in your head. Every time you weigh yourself at home, you can add in 2 more pounds to get a more realistic picture of what you weigh. Or if you can find the instructions to the scale, maybe there's a knob or a button that you can recalibrate it. So let's say that we have a mass that is 8.250 grams, and we're measuring it with balance Y, and we're measuring it several times. So a lot of times it's coming out to be 8.250 grams, but there is a limitation to every instrument, so every once in a while it can be plus or minus 0.001 grams. So if you measure something a bunch of times, you're going to get a few that are a little bit off. So every once in a while you might even get one that's 0.002 off from what the true value should be. But so this is a random error. We have some higher measurements, some lower measurements, and we have a range that's pretty much within 0.001 of the true value. So let's contrast this with a different balance. This balance just goes 2 places past the decimal, and so most of the time it's giving the value we expect. Every once in a while it's off a little bit, by 0.01 grams this time instead of 0.001. And then maybe every so often we have a measurement that's 0.02 off. So again, we have a fairly even distribution of some measurements too high, some measurements too low, but just because of the difference in this instrument, it has a different amount of random error. So this is plus or minus 0.01 grams for the most part, maybe a couple of outliers, and this one is plus or minus 0.001 grams. So balance Z, we have a similar thing happening, maybe a similar level of precision, plus or minus 0.001 grams. However, you'll notice that all of the measurements that are being taken by balance Z are too low. Remember, this is supposed to be something that has a mass of 8.250 grams, and this one is centering most of the measurements around 8.220 grams. So it's off by a little bit. The precision is comparable to the precision of balance Y. It has the same level of random error as balance Y, but in addition to this random error, which you can't get away from, balance Z also has some systematic error. Perhaps it needs to be recalibrated, or perhaps it's not level on the bench. It needs to be adjusted in that way, but there is a slight problem with balance Z, and it's pushing all of the values in the same direction. All of these values are a little bit too low. So when we are doing an error analysis, we are looking for possible sources of systematic error. What could be pushing the results too high or alternatively too low? And so sometimes we're asked what could be a possible source of error in the experiment. And a lot of times a student will write something kind of vague like this. I could have written the measurements wrong, and then that would have had a bad effect on the calculations because they would be wrong too. That's why it's important to be very careful when taking measurements in science. Well, I mean, you know, there's complete sentences as an answer to the question, and the grammar and spelling look pretty good, but there's not really very much analysis going on here. You know, this might be okay for elementary student, but as far as analyzing what went wrong, you didn't really have to even do the experiment or read the experiment to come up with this kind of answer. So you're not really analyzing what specifically was done in the experiment that could be causing an error. There are some other things that students might think to put that are not really the kind of error that we're talking about. So remember, we want a systematic error, something that's going to skew our results in a specific direction, and something that can be corrected for, like a recalibration or something like that. So writing things down wrong and using wrong formulas to do calculation is something that's not really predictable. We want something that's more subject to being analyzed and possibly corrected for. So these things I think would count as mistakes, not really error or uncertainty. So how do we go about trying to find a source of systematic error if we don't really have any other ideas besides writing down the numbers wrong? So as you perform the experiment or read through the experiment, if you're doing a remote experiment or watching a video of an experiment, think about the things that you have to be careful about when you're doing it, and use your imagination to visualize what would happen if you did them differently or did them an incorrect way. Also, if the people around you, if you notice anyone else is struggling or making errors with things, or if anyone else's numbers are way off, and you know, you could maybe think about what they're doing, think about whether that's something that you can use as an idea for errors in the lab. Also, if you notice the professor cautioning students, a lot of times we see the same errors again and again, and so if there is something called out that you have to be very careful to do something a certain way, just go ahead and think about what would happen if you didn't do it that way. Once you've thought of a possibility, then go ahead and think about what effect that error would have on the results. So not just whether it would make the measurement itself be pushed higher or lower, but then that error in the measurement, in that number that you've taken that is a little higher or lower than it should be, follow that through the calculations and see if it's going to affect your results and whether that effect is going to be higher or lower. Sometimes it's helpful to make up a number. So if you have a number that you got for the experiment, think about if you did something differently, would the number you got be higher or lower? Maybe even make up an actual number that's higher or lower, and then do the calculations on that number and see what happens, see which things are pushed higher and which things are pushed lower. So some people tend to just kind of pick something, oh, I spilled something, and then that's going to be lower, and then everything's going to be lower. You just have to think things through. So for instance, if you spill something that you're trying to weigh, so if you have a beaker and you weighed the beaker empty and you try to put a bunch of solid into that beaker and you're very messy about it and you spill it all over the bench, well, I mean, you should clean that up, but the stuff that got into the beaker, the stuff that you're actually going to use, that's what you're going to weigh on the balance. The stuff that you spilled all over the counter doesn't get weighed on the balance, and so that particular spill is not going to affect any of your results. So just because you spill something, it doesn't mean that it's going to make all of your numbers lower. It might make, if you did spill something, it might make some numbers higher and some numbers lower, depending on when you spilled it, what you measured before and after you spilled it. Even if you go through and figure out that this particular spill that you're thinking of would make all your numbers lower and all of your calculation results lower, at least list that and tell how everything is going to be pushed lower by this error. So in general, what we want is some analysis of the errors, some thinking about the experiment, some following through these errors with the calculation. And so if you read your error analysis and you realize that it could have been written by someone who has no familiarity with the experiment whatsoever, then you're not analyzing what you did in your specific experiment. So that's not enough analysis. So let's try to think of some examples of possible errors that could happen. So here is a fairly straightforward procedure, sort of a beginning of the semester kind of thing, where we're learning how to measure things. And so in lab, we're supposed to measure the length and width of a piece of paper. And there's a little caution in the instructions to be sure to start at the 0 line of the ruler, not at the edge of the ruler. So here is our ruler held up against a piece of paper. We are following the instructions starting at the 0 line, and then we get a measurement of about 13.56 centimeters. I just wanted to point out that these numbers are centimeters. Even though this says millimeter, the millimeter refers to the fact that the lines are 1 millimeter apart, because the numbers are every 1 centimeter, but the lines are every 0.1 centimeters, and 0.1 centimeter is a millimeter. So some of our rulers do say that, but these numbers are in centimeters. All right, so what if you did start at the edge instead of the 0 line? How would that skew your results? And this is a source of systematic error because it skews the results in one particular direction, and you can figure this out. Maybe you can visualize and predict which direction. So if you imagine this ruler just being shifted to the right while the paper stays in the same place, the other end is also getting pushed this way. So remember, the paper edge was over here before. Now we've pushed the ruler to the right, and now the paper edge is at a smaller number on the ruler. So this would probably be read as about 13.24 centimeters. Remember, it should be 13.56 centimeters. So the length that we're getting is too small when we introduce this systematic error. And anything we measure this way is going to give us a result that's too small. So if we also measure the width this way, the width is also going to be too small. And since the area is length times width, if you have a smaller number for the length, it's going to have a smaller area as well, because you're multiplying something by a smaller number. All right, I thought of another possible source of error, maybe something a little bit unusual. So if you happen to have a really sad looking ruler like this, we have a ruler that's been worn down quite impressively, And so it no longer has a 0 line available. It looks like we're starting at about the 0.4 centimeter line. So we're starting off on the other side of the 0 line. It's kind of like the ruler got shifted to the left. And so when you read the measurement, which remember the paper should have been about here, but since we pushed the ruler in this direction, the paper is now coming close to 13.9, maybe 13.89 centimeters. And so remember, it was supposed to be closer to 13.56 centimeters. So this measurement is too big. And then if our length is going to be too big, since we're multiplying it to get the area will also be too big. All right, so that last example reminded me of a way to correct the problem. It reminded me of a worn out tape measure that my grandmother used to use for sewing. The edge was just all frayed, and so you couldn't really use the 0 line. And, sometimes carpenters with very worn out tools will use this trick as well. And that you could start at the 1. If there's no 0 line because it's too frayed or too worn down, you can start at the 1, and just remember that if you're starting at the 1, you have to subtract that again. But if we remember to subtract that 1 from the measurement that we read, we get 13.58. So that is much closer to the measurement we were expecting of 13.56. It's kind of like if you, instead of starting a race at the 0 line, you start at the 1 mile line. Then if you go from 1 to 14.58, you've gone 13.58 miles. So that would be the same as if you started at 0 and went to about 13.58. Another example of correcting something, if you have a scale and you know that whenever you go to the doctor's office, you weigh 2 pounds heavier than what you think you do according to your home scale, and you start to suspect that your home scale is 2 pounds too low, then if you want to have a more accurate idea of what you weigh, you can just add 2 pounds in whenever you weigh yourself. Or possibly you can find the instructions for your scale and see if there's a button or a knob that you can adjust it with. So if you discover a systematic error, sometimes there is a way you can think to get around it or to correct for it. All right, here's another possible systematic error. So here's a procedure for what we are supposed to do. We are measuring the density, or we are calculating the density of a solution. And so here is our procedure. We're going to zero the balance with an empty beaker and use a graduated cylinder to measure the volume of some of the solution that you were given. And it says to be sure to read the bottom of the meniscus. And then you add the solution to your beaker and weigh the beaker with the solution in it, and then calculate the density of the solution. So here's our graduated cylinder. I picked a fairly thin graduated cylinder so that the meniscus would be more pronounced. The meniscus is the curve that happens when you have water or an aqueous solution in a glass container. Just water has a strong attraction to glass, and so you get this little smile. And the convention is to read it at the very bottom of that curve. This curve is called the meniscus, and the graduated cylinder has been calibrated so that you read the meniscus at the bottom. So the correct reading here, it's just below 7 milliliters. Each of these lines is 0.1 milliliters. You have 6, 6.1, 6.2, 6.3, all the way up to 7. And so the correct reading here, since it's between 6.9 and 7.0, I think it's closer to 6.9, so I put 6.94 milliliters as the correct reading. However, if you were trying to read the top of this meniscus, it definitely seems like it's above 7. It's actually above 7.1, so you might record something like 7.18 milliliters. And graduated cylinders are designed to measure the amount of water that they contain. So you're doing one volume reading and then you're dumping all of this water into the beaker to get the mass of it. And this one reading that you have is the volume that you say you are putting into your beaker. So our incorrect reading is going to be too high because we're reading the top of the meniscus when we should read the bottom. And we should take a look at how the error propagates through the rest of the experiment. So after we do that incorrect volume reading, we pour that amount of solution into our beaker and we get the mass. And the mass of the solution that we get is not going to be affected by the fact that we read the graduated cylinder wrong or that we read the meniscus wrong. The same mass of solution is going to result whether we read that solution as 6.94 milliliters or 7.18 milliliters. So I'm just going to use M as our mass. That is not going to be affected by our error. The volume is affected by our error. The correct reading is 6.94. The incorrect one is higher, 7.18. So this number that's too high is in the denominator. And so if we have a number that's too high in the denominator, that's going to make our answer smaller. Larger denominators make this a smaller result for the density. If the volume is too large, then the density that we calculate from that volume is going to be too small. So it's not usually good to make a generalization like, oh, it's too big and everything's going to be too big. Well, sometimes something that's too big makes other things too small. Here's something else that could happen with an error reading the meniscus. This time, instead of a graduated cylinder, I thought we might be adding the volume using a burette. So this is what a burette is. It's a glass tube with a stopcock on the bottom, and you use it by dispensing liquid. You open the stopcock and you can add it to a beaker or to a reaction. Unlike the graduated cylinder, you are not concerned with how much liquid is in the entire burette. The way that a burette is used is that you take an initial reading and then you add some liquid to wherever you want to add it to, and then you take a final reading. And the difference between those two readings is the volume that you have added to your reaction or to your beaker. So the volume that you've dispensed is what you're concerned with, not the volume that's in there, the volume that you take out of there to use. And that would be equal to the final volume reading minus the initial volume reading. So it's kind of like if you were starting a race and you jumped in to the race and you started at the 2.5 kilometer mark and you ran until you were tired of running, and it ended up that you stopped running at the 4.7 kilometer mark. So the distance that you ran would not be either of these numbers. It would be the difference between the numbers. So you actually ran 2.2 kilometers. But it doesn't matter how long the entire race was, just like it doesn't matter how much liquid is in the entire burette. What matters is where you started and where you ended. That's how you know how far you've gone. So what if you make your meniscus reading error using a burette? So the reading that you're supposed to take is the bottom of the meniscus. You have to be a little bit careful with the burette because the larger numbers are at the bottom and the smaller numbers are on top. So instead of saying this is 3 and this is 3.5, that's not true. This is 2 and this is 3. This is 2.5. So going down from the 2, it's 2.1, 2.2, 2.3, 2.4. It's between 2.4 and 2.5, so this would be read as 2.47 milliliters. Similarly, after the liquid has been drained, you're ending up here. It's between 6 and 7. This is 6, 6.1, 6.2, 6.3, and this is 6.6. This is 6.7. It's very close to the 6.7. I might put this as 6.69 or 6.70. And then the volume that has been dispensed is the difference between these two numbers. So 4.22 milliliters was used when I went from here to here. If you read the top of the meniscus, in this case, since the smaller numbers are on top, your numbers are going to be a little bit too small. But both numbers are going to be a little bit too small, and since the meniscus has about the same shape, they're going to be too small by the same amount, about 0.18 milliliters too small. But if both of your readings are 0.18 milliliters too small, then the difference between the readings is going to give you the same volume. So if you made this error, this type of error, using a burette, as long as you made the same kind of error both times, you would get a very close result to the correct readings. So every once in a while, a systematic error, if you happen to be lucky with it, it might not even affect your results. Not that it's recommended to read things the wrong way, but in this particular case, it just so happens that you got lucky and the error didn't affect your final result at all. And then if this were used in a density calculation, since there's no difference in the volume, then the density result that you get would not be different either. All right, so why is it important to be able to identify possible sources of systematic error and also know which direction the error would be pushed by that particular error? Well, first of all, we pointed out that you might be able to correct for that error. If you knew that your scale gave a reading that was 2 pounds too small, then you could always add 2 pounds to get closer to the right result. So if you know which direction your scale is off, just knowing that it's off isn't going to help you. But if you know that it's off in a number that's too low and you know by how much that is, you can correct for it. Also, if you're working in a lab and you suspect that you're getting results that are too high, or if you think of 6 possible errors that you might have made in the lab, but 3 of them would make your results too high and 3 of them would make your results too low, you would investigate the errors that make your value too high first. So that is useful to know which of the possible errors that you thought of are more likely because you know which ones push your results too high. In summary, when we are trying to think of possible sources of error in our labs, what we are really trying to do is thinking of a source of systematic error, not some random error so that the answer is to buy a more expensive balance, or a mistake where the answer is to be more careful. We want something that would cause all of our measurements to skew in the same direction, either all of your measurements being too high or all of them being too low. And then also following that result through the calculations and see if it would make your calculated value too high or too low, because these don't always match, like we saw in our density example.